Hi, so this video we've looked at already in the last couple areas bound between the x-axis and the y-axis. So we're going to be looking at areas bound between different curves. So when we say curve, we just really mean any can be any kind of function or equation, right? So we could like something that's actually curvy, like a polynomial or a trig function, something like a parabola, but even straight lines we're considering curves as well. So we might have to use some of our skills from x-axis and y-axis bound curves, but what we're definitely going to have to do with all of these, like before, is to draw a diagram. So let's just start with question 1. Find the area enclosed by the curves y equals x minus 2 all squared, the x and y axes. So we've got the curve y equals x minus 2 all squared. So x squared is a, here we go. Oh. X squared is a parabola, and what's the effect of the minus 2? This shifts 2 to the right. So let's sketch some x and y axes. So if it's a parabola, let's move 2 to the right. The vertex is going to move to 2. Down the bottom here is obviously the x-axis, and up here is the y-axis. So the area enclosed by these three curves will be this region in here. Now we could find, for example, what this y-intercept is, but it's not really of interest because since this is essentially going from 0 to 2, right? Once we've drawn up the diagram to visualize it, it's clearly just an area below a x-axis, right? So if I drew up this diagram 2 videos ago, this should have been doable. The only difference here is just the wording that it's bound between the x and the y-axes. So to find the area here, we'll find the definite integral from 0 to 2 of x minus 2 squared dx. So the integral of x minus 2 all squared, you could expand this out and then integrate term by term. But since the function inside x minus 2 differentiates to 1, if we think of this as a reverse chain rule, x minus 2, the whole thing's squared, so add 1 to the power is 3, and divide by the new power of 3, and also divide by the derivative of the brackets, which is 1, so it's unchanged. And we're integrating from 0 to 2, so we'll plug in 2 and subtract, plugging in 0. So 2 minus 2 all cubed is 0, cubed over 3 is 0, minus negative 2 cubed is negative 8, and minus becomes 8 on 3 square units, whatever they are. Right, and it came out as a positive number because it was above the x-axis. So hopefully nothing too tricky for that one once we've got the diagram drawn up. Alright, 2. We're looking between y equals x squared, y equals x minus 4 squared, and the y-axis. So y equals x squared is a parabola, and what does the minus 4 do to the parabola? It shifts it 4 to the right. So let's draw up a sketch with both these parabolas in it. So y equals x squared will be there, and if we've got another parabola, move 4 to the right. So the area enclosed or bound between these two curves and the x-axis down the bottom here, right? So between these curves and the x-axis is going to be this portion in here. So now, if we knew what this point was here, we could find the, sorry, I'll just label which is which. If we found what this point is here on the x-axis, we could find the area up to, we'll draw this. Right, we could find the area under x squared up to this orange line, and then find the area under x minus 4 squared from the orange line up to 4. So, how are we going to do that? Notice this is a point of intersection, so we can find the point of intersection by equating the equations. So if we've got y equals x squared and y equals x minus 4 squared, the point of intersection is where they're equal, so let's set them equal to each other. And now we'll solve this equation, and it'll be for x, so we'll then figure out the x coordinate here. So if we expand out the perfect square, we get x squared minus 4 lots of x doubled is 8x plus the other one squared. Now we've got x squared, positive x squared on both sides, so if we minus x squared from both sides, they'll cancel out. Negative 8x, if we add to the other side, is 8x equals 16, and divide both sides by by 8 is x equals 2. So that means we know that this spot in the middle here is x equals 2. Which kind of makes sense if you think about it geometrically, right? The parabolas are symmetrical. They're the same steepness because they're both just x squared. They haven't been multiplied by a coefficient out the front. So if they're equal and they've been spaced out by 4, they're going to cross at the halfway point too. Alright, so how can we find the area? Well, we can find the area by finding this green piece here, which is the area from 0 to 2 of x squared. Right, that's the green bit there. And we'll add it to, we'll add this pink piece here, which is the area from 2 to 4 of x minus 4 squared. Right, so that's where each of those pieces have come from. So if we integrate x squared, we get x cubed on 3. This is going from 0 to 2. Plus, just like before with x minus 2 all squared, right, we've got x minus 4, the derivative is 1. So we can integrate this by adding 1 to the power and dividing by the new power. So x minus 4 all cubed on 3, and this is going from 2 to 4, and now the rest is just a matter of substituting in and evaluating. So we've got 2 cubed on 3 minus 0 cubed on 3 plus 4 minus 4 cubed on 3 minus 2 minus 4 cubed on 3. 2 cubed on 3 is 8 on 3 minus 0 plus 4 minus 4 is 0 cubed on 3 is 0. And then we've got minus 2 minus 4 is negative 4, all cubed is negative 8 on 3. So we've got 8 minus minus, so plus another 8 on 3 is 16 on 3 square units. Okay, so again, like hopefully again this was emphasized throughout, is you really got to think geometrically how you can kind of manipulate these to break certain things up into kind of different pieces that you can recognize, that you can calculate. Alright, 3. Notice here, we're now getting less and less information. Before we had, you know, three bits of information here: a curve, the x and the y-axis. In question 2, we had 2 curves in the x-axis. Back with all the ones we did in the last 2 videos, bound by the x and y-axis, implicitly there was one piece of information, the axis, and then there was normally a curve and 2 points. Here we've got just 2 curves, y equals x squared and y equals x plus 2. So let's draw a diagram of this and see what it looks like. So y equals x squared will just be a parabola, and y equals x plus 2 will be a straight line. Plus 2 will be the y-intercept, and it's got a gradient of 1. So it's going to look something like this. So the reason that's all the information we need is because when we graph these 2 curves, you can see that they automatically create a region together. So how are we going to find this area here? Well, we can find this area by subtracting the curves, right? If we find the area, assuming we know these points here, which we'll be able to figure them out in a moment, we can find the area under the x plus 2 curve, will be like this trapezium shape, and then we can subtract the area under x squared, will be all these other gaps in here, and we'll be left over with this enclosed region here. Right, so if we find, for example, what I mean is this yellow region, right, and then we subtract, color is in blue, makes it, if we subtract this green region here, then we'll be left over with the area between the 2 curves. So again, we've got to find out, well, what actually are these x coordinates here, so we can integrate x plus 2 from here to here and integrate x squared from here to here as well. Well, again, these are the points of intersection. And how can we find the x coordinate of the point of intersection? By equating the curves, and because we only need the x coordinate to integrate bound by the x-axis here, we don't need to even worry about the y coordinate. So let's equate x squared. When does x squared equal x plus 2? So since we've got x squared and x, let's collect everything to one side and make 0 the subject. So minus x from both sides and minus 2. So this is fairly easily factorable because you've got a product of negative 2, a sum of negative 1. So your factors are negative 2 and 1. X minus 2, x plus 1. And using null factor law, since these 2 things time together to give 0, either this one equals 0, which is when x equals 2, or when x equals negative 1. So, how can we find the area? Now that we know these points, we can find the area of underneath the line on the curve on the top, which is a straight line here. So the area from negative 1 to 2 of x plus 2. And we can subtract the area under x squared. Right? If we subtract the area under x squared, will be these two pieces here and here, and then we'll be left over with that area. Now, since we're integrating across the same range, we could do these two separately, or we could combine them all into one integral. X plus 2 and then minus x squared. Or there's no issue with you can integrate this over this range, integrate this over this range, and subtract them, and you'll get the same thing. But just because I've noticed that we're going from here to here, we can just combine them and do it all in one go. So if we integrate x, we add 1 to the power, divide by the power. 2 is a constant, so it integrates to 2x, and minus x squared integrates to add 1 to the power, divide by the power, new power. And we're going from -1 to 2. So we'll sub 2 in, 2 squared on 2, plus 2 times 2 minus 2 cubed on 3. Now minus, make sure you put all this in brackets, because if you just write minus and then start doing this, you'll plus this when it should be minus, and you'll minus this when it should expand out to be a plus. So we've got -1, oh, I'm going to fit this, plus 2 times -1, minus -1. Cubed on 3, and at this point let's just put this in our calculator. What's that? 2 plus 4 minus 8 on 3 minus a half minus 2 minus plus a third, all in brackets. Should be 4.5 square units. Right, so this one, because the two equations automatically created an area, that's why we didn't need all that other information, but we still did need to find these x coordinates. So again, when you need to do that, we want to find when are these equations equal, so we need to solve them, we need to equate them. Right, and again, you got to think geometrically of how can you get this piece. Well, you can get it by doing the big piece, the area under x plus 2 from here to here, minus these small pieces here, which are given if you do the area under x squared. Alright, question 4. I better move this back. Y equals x squared minus 4, and y equals 5. So what does minus 4 do to the parabola? This moves it down by 4. Whoops. So here's x squared minus 4. It's been moved down to -4. And the other line is y equals 5, which is a straight line. Should pass through 5. And again, these two automatically enclose a region here. So, how are we going to find this? Well, there's a few ways that you could do this. So, one is that you could find the area. First of all, we could find these x-intercepts here, which will be, when does x squared minus 4 equals 0? When x is 2 and -2. So we could find the area enclosed whoops, should be there too. We could find the area enclosed by x minus 4 squared from x equals negative 2 to 2. Now remember, because it's below the x-axis, when you calculate that it'll be negative, so you've got to make sure you take the absolute value. So that's how you could get that piece there. And then this piece above here, you could find the area of this rectangle here, where these points are. And then what you could do is you could subtract away the area from here to here, and from here to here, from the under the curve of x minus 2 all squared. Now, okay, so what I'd suggest doing though is, again, try and think geometrically. I think you can make your job a lot easier if you do a small manipulation which will make the problem look a lot easier. So if we move this whole thing up by 4, it's going to be sitting on the x-axis. Right, let's move everything up by 4. So if we move everything up by 4, then the negative 4 moves up by 0. So now we've got the equation, we've moved it, right? This was the graph of x squared moved down by 4, so if we move it back up by 4, it'll sit there, up to x squared. And then if we move the line y equals 5 up by 4, then it'll be up to y equals 9. Right, so this will still be the exact same area here, but why is this easier? Well, now we've just got an area, right, if we find these values here, right, we can find the area of this rectangle here, right, and subtract away the area under x squared, and then we'll be left with this area here. Right, so how can we find these points? Again, this is when does x squared equal 9? Or when does x squared equal 9? When x equals plus or minus root 9, when x equals plus or minus 3. So the area here will be the rectangle, which is, well, from negative 3 to 3 is 6, so 6 by and 9 high, so 6 by 9, minus the area under, we're just doing the area under x squared, right, we're going to subtract away these pieces here, and we're going from negative 3 to 3. Now, just whenever we're going from negative value to another value, your brain should be twigging, oh, hold up, do I need to do anything here? Because remember, if this was an odd function, these areas would subtract out and cancel each other out. But it's okay because it's an even function. This will be fine to just go ahead and integrate and plug the values in. So 6 by 9 is 54, minus the integral of x squared is x cubed on 3, from negative 3 to 3, minus, now because we're minusing, I'm going to put it in brackets before we plug these numbers in, so putting in 3 cubed on 3, minus negative 3 cubed on 3 is 54, minus 3 cubed is 27 on 3 is 9, minus 3 cubed on 3 again is 9, but minus negative 9, so that's 18. 54 minus 18 is 36. square units. Right, so again, there is different ways you could do this. You'll remember when I introduced areas enclosed by the y-axis, I showed 3 different ways of doing the same problem. So there's going to be lots of different ways you can do these problems. But again, try and think, how can I do this easiest by geometrically moving it around, rotating it, doing something with it. I think it's personally easier to find just this basic rectangle minus an area bound by the x than having to look at this graph here where it's got pieces above the x-axis and below the x-axis and either side of the y-axis. I think it's easier to visualize and calculate this equivalent area, but that we've just kind of pushed it up. Okay, last one, y equals x squared, y equals 4, and y equals 9. Alright, so first thing to always do is draw a diagram. So this is x squared, this is y equals 4, and this is y equals 9, and these create this region in here together. Oh, 1 second. Okay. So again, let's think about the different ways we could approach this. Because we've already got the y values here, we could turn this into a function of y and integrate it as a function of y from 4 to 9, and then we could double it. We could integrate, if we found these x coordinates, we could go from here to here and subtract away these pieces, these little pieces here, and then there's a rectangle below. So again, there's going to be different ways you can process and think about it. Maybe just to mix this up, I'll change and do this as a function of variable y. So if we've got y equals x squared, and we do opposite of square is square root to both sides, we've got x equals plus or minus root y. Now this isn't really a function of y, because if it's a function, then, well, the problem is you've got plus or minus, it's got 2 outputs, so it's not a function. So obviously these 2 pieces here are going to be symmetrical, right? X squared symmetrical, and then we're going right the same distance from here to here, the same distance, these points. So if we just find, say, one of these pieces here, then we can find one piece and double it. So that piece there is the positive part of root y. So let's integrate positive root y, which is y to the half, and we're going to go from y equals 4 to 9, and that'll give us the yellow piece, right? And we're integrating with respect to y, and then we can double it to find the other piece, right? So we can find the other half here by doubling it. Okay, so we've got 2 times integrating y to the half with respect to y is add 1 to the power, divide by the new power, and then y cubed with over half in the power is the square root, and dividing by a, oh, you can't see my mouse, Dividing by a fraction is same as multiplying by the reciprocal, so 2 over 3. Going from 4 to 9, and then we're doubling whatever that is. So we've got 2 times root 9 minus 2 times root 4 cubed, and then we're going to times that by 2. So this is 2 times, we've got 2 times root 9 is 3, cubed is 27 on 3, minus 2 times root 4 is 2, and cubed is 2 times 8 on 3, times that all by 2 is 25 1/3 square units. Right, so again, hopefully I've emphasized this throughout all 3 videos this week about finding area bound between x-axis, y-axis, and just multiple curves. Is try and be flexible in having lots of different approaches. So you should practice different ones, and you got to think geometrically, right? Like for example, this last one, I won't solve it this way, but I'll just show you what I meant, and maybe you can have a go at solving this another way. Right, is be flexible in attempting, different ways of breaking the shape up into pieces, right? If you find this big rectangle here, right, which will be from -3 to 3, and where are these points here? This will be 2 to -2. So if you find these purple pieces here, right, and you've got the big orange box, and we've got the this other rectangle under here. Well, how can you find the area in blue? Well, you can do the big orange box minus the yellow box, and then subtract these two times these purple pieces, which will be an integral from 2 to 3. Right, so you can do, if you want to have a go doing the same problem with a different approach, if you do it correctly, you should get 25 1/3 square units. You should get the same thing. So feel free to have a go at that. Try get used to doing different methods, so you have lots of different possibilities in your toolkit. Alright, that's it for this video. Bye.